Alrighty, so this video we will be doing several examples on analyzing circuits using the nodal analysis technique. Last video we saw how to use this technique. Basically, you're given a circuit. You first choose a ground. And what that means is find a place on your circuit, choose a place that you will define to be at 0 voltage, and that's called the ground. And so from then on, all voltages that you calculate will be relative to that ground. So if you calculate a voltage of 3 at node A, and then later on you find out that the location of the ground really was at 10 volts instead of 0, then you just add 3 to 10 to find out that the node voltage at A is actually 13. So you choose a ground. Once done, you label the nodes. Once you've labeled the nodes in your circuit, you show the currents going into or out of the nodes. Then you write the Kcl equations, and the Kcl equations are the currents coming in to the node minus the currents going out of the node must be equal to 0. So I in minus I out is equal to 0. And lastly, rewrite currents as V over R. Once you've done this, you're going to have some set of equations whose unknowns are voltages, the voltage at node A, voltage at node B, and so on. And so you use algebraic techniques to calculate these unknown voltages, and then you get your information. So with this video, I want to do a few examples just to show how this works. We already saw some in the previous video, but we're going to do some more complicated ones here. So let's take the first example. Say we have this as a circuit. All right, and we have, let's say 5 amps, 10 amps, and this could be 2, 4, and 6. And let's say I want to know what is the voltage at A and what is the voltage at B. Find VA and VB. Okay, so the first thing you notice is this circuit has current sources in it. And a lot of times, if you see that, that's kind of telling you, hey, maybe you want to try nodal analysis as the technique instead of something like loop analysis. So we're going to do nodal analysis. What's the first step? First step is to choose a ground. And as usual, down here at the bottom, I'll choose this to be the ground. So that red mark there defines the ground. So all of this down here is the ground. That means that point is labeled as 0 voltage. Next step is to label all the nodes that we need. Well, obviously, A will be a node, and B will be a node. we'd have a C, but C is the ground down here, and so we don't need to call it C, we just call it the ground. So there we go, we have two nodes in this case. Next step is to show what the currents are coming into and out of the nodes. So here at A, we have this source coming in. I'll call that I1. We'll have this one going out, I2. And we'll have this one going this way, I3. What about at B? At B, notice the 5 is coming out of B to go to A, so that's still there. But I already called that I1, so I just relabel it I1. It's the same current. It goes out of B and into A. It doesn't change its name. Likewise, I3 that's going from A and hits the 4 ohm resistor and goes to B, that's all I3. So this is still I3 over here. I've got this 10 coming up from the ground going into B, so there is, I'll call that I4. And then lastly, the current that goes from B down to the ground, I'll call that I5. Basically, when you have a node, every wire that comes out of the node has a current. So you just label them 1, 2, 3, whatever. You get to choose the direction you think the current's moving. If one of them is a current source, then obviously you know the direction. But other than that, you can arbitrarily choose, do you think it's coming into the node or going out of the node? If you happen to choose the wrong way, you'll just get a negative current later on. No big deal. All right. So I've now labeled the nodes, showed the currents coming into and out of. Next is to do my equations. So let's do node A first. And I'll do this kind of in a very organized manner. Node A. Sometimes it's helpful to show what node A looks like. Here was A. And what did we have? We have I1 coming in like this, I3, and I2. Right? That's what node A looks like. So, currents coming in are called positive, currents leaving are called negative. So I have I1 minus I2 minus I3 is equal to 0. That's the Kcl equation for node A. And now what I want to do is I want to rewrite these I's. Either I know the number, I know what the current is because it's a current source, or if I don't know what the current is, then I rewrite it as V over R. So let's see. I1, do I know what I1 is? Yes, I1 is the 5 amp source, so I1 is 5. Minus. Now I'm at I2. I2 is that current leaving node A going downwards towards the ground, so it's going from A, so VA, minus, where is it going to? The ground, 0. So it's V divided by R. What is the R? It's 2. So now I2 is done, minus I3, same kind of a thing. Do I know what I3 is? No, it's not a source, so I change it to V over R. Where is it starting? It's starting from VA, and it's going towards VB. So VA minus VB divided by the resistor, which is 4. And so now I have I1 minus I2 minus I3 is equal to 0. So that equation's done. I can simplify it, which is what I'll do now. To simplify this, usually what you want to do is multiply by a number that will cancel out all of the denominators. So it has to be a number that's common to all of the denominators. In this case, I have 2 and 4. So 4 is common. So I'm going to multiply this whole equation by 4. And so that leaves 20 minus the 4 cancels out the 2 and makes it a 2. So I have 2 VA. And then the 0, of course, is 0. Then I have minus. The 4 cancels the 4, so I'm left with VA and VB. Now, what do I want to do? I already know algebra stuff is going to be coming up, so let me get this into standard form, where I have all the unknowns on one side and the numbers on the other. So I have minus 3VA plus VB is equal to minus 20. And there's my equation for node A finished. Now I want to move on to node B. Node B. What does node B look like? All right, here's the node. I've got I4 coming in, I5 leaving, I1 leaving, and I3 coming in. That's what the node looks like. All right, so I have minus I1 plus I3 plus I4 minus I5 is equal to 0. Remember, all the arrows that come in are positive, the ones that leave are negative. And again, any of these that I know the number because it's a source, I plug in the number. Whichever ones I don't know the number for, V over R. So I1, do I know what I1 is? Yes, I1 is a 5 amp current source, so it's minus 5. Plus I3, do I know what I3 is? No. So, what was I3? I3 was the current that went from A, so VA, to B, minus VB, divided by the 4 ohm resistor. Then I have I4. Do I know what I4 is? Yes, it's the 10 amp source, so it's 10. And then the 5. Do I know I5? No, so it's V over R. Where does it start? I5 comes from B, goes to ground, divided by 6 is his resistance, is equal to 0. And now, that's my equation for node B. Just as before, I want to simplify this down as much as possible, so I want to get rid of the denominator. What number is common to both 4 and 6? Well, the smallest one is 12, so I can multiply everything by 12. So 12 times negative 5 is negative 60, plus 12 divided by 4 becomes 3, so it's 3VA minus 3VB. 12 times 10 is 120. 12 divided by 6 gives me 2, so it's 2VB. Okay, so there we go. Again, standard form, all the unknowns on one side, all the other numbers on the other. So what do I have? 3VA minus 5VB is equal to negative 60. And so there's my equation for node B. At this point, all of the physics is over with. I've done all my equations. I've gotten down to 2 equations with 2 unknowns. All that's left is to do the algebra to calculate A and to calculate B. Again, you can do this any way you want. Usually I use Cramer's rule. Here I'll do it with substitution, just because I don't always do it that way. So I'll do this in, let me do this in green, just so it doesn't blend with the blue here. I'm going to take this first equation, node A's equation, solve for VB. So I have VB is equal to 3VA minus 20. Now I take that VB and I'm going to plug it into node B's equation, where VB is. So I have 3VA minus 5 times VB, which is 3VA minus 20, is equal to minus 60. Clean this up. We've got 3VA minus 15VA plus 100 equals minus 60. Let's see, minus 12 VA is equal to minus 160. So we get VA is equal to 40 over 3. So I now know what VA is. VA is 40 over 3. That's one of my answers. To get the other, VB, which is right here, VB is 3 times VA, but VA is 40 over 3, minus 20. The 3's cancel, so I have 40 minus 20, which is 20. There's my VB. And there we go. Here we have an example, a nodal analysis problem. Given a circuit, it has a bunch of current sources in it, and I want to know what is the voltage at these particular points. In order to do it, first step, label a ground or choose a ground. Label the nodes in your problem. For each node, show the currents coming in and the currents going out. Write down the equations for each node for those currents using Kcl rule, which says currents coming in minus currents going out is equal to 0. Once you have the equations, rewrite the I's as V over R using Ohm's law. And now what you have is a set of equations with VA and VB and VC and so forth as your unknowns. At this point, you do whatever mathematical technique you know how to solve multiple equations with multiple unknowns. In this case, I use substitution. And you calculate your unknown voltages. Let's try another example. Example 2. Okay. Let's say we have this. All right, and I'd like to find the voltage at A and the voltage at B. All right, so very similar question, a different circuit sitting here, so let's go through the same process. First step, choose a ground. Okay, here's my ground. All of this stuff down here is the ground. Next, nodes. Well, obviously A and B, because I want to find voltage at A and voltage at B. So that's easy. Now what we want, currents. Okay, well, let's look at A first. Let's assume, how do we want to do this? We'll have I1 this way. Oops. We'll have I2 going out that way. I3 going down this way. And I4 going off to the right. Okay? And then for B, what do we have? Well, I2 went up from A, went through the 2, and came down to B. So that's still I2. I4 went straight to the right, so that's still I4. This 3 amps coming in this way, I'll call that I5. And I6 will be this one coming down this way. All right. I've shown my currents. Now I start on my equations. So let's look at A first. Node A. What's node A look like? Here's the node. I've got I2 going up, I4 going to the right, I1 coming in from the left, and I3 going down. All right, so we have I1 minus I2 minus I3 minus I4 is equal to 0. That's my Kcl equation. Replace everything with V over R or the current source or whatever we have. So let's look at I1 first. I1 is a current that's coming into A. Where did it come from? It looks like it came from the ground. Right? Here the ground sent up I1. It went through the 10 and just kept going. Hit node A. So for I1, we started at the ground. Oops, not black. We'll do it in blue. So we started at the ground, and we got to A, so 0 minus VA, over the resistor, which was 10. I2. We went from A, go through the 2, and got down to B, so VA minus VB, over the resistor of 2. I3, we start at A, we go down to the ground, and we go through the 5 ohm resistor. And in I4, well, that's the current source of 6, is equal to 0. So there's his equation. As usual, I see here this equation has two unknowns in it, A and B. Because of that, I can't just solve it, so I'm going to be doing some algebra stuff later on. So let me simplify this equation. Get rid of the denominators. What do I multiply by? Well, let's see. I've got a denominator of 2, 5, and 10, so I need something that's common to all of them. 10 is common to all of them. So I'll multiply everything by 10. The first term, 10 times, or 10 divided by 10 becomes 1, so I have 0 minus VA. The second term, 10 divided by 2 gives me 5, so I have minus 5VA plus 5VB. The third term, 10 divided by 5 gives me 2, so I have minus 2VA and then 0. And then the 6 times 10 gives me minus 60 is equal to 0. There's my equation. I want to simplify this, get it in the standard form. So minus VA minus 5VA minus 2VA is minus 8VA plus 5VB is equal to 60. And that's all I can do with him. So there's my equation for node A done. Now we go on to node B. What's node B? Here's the node. I've got I2 coming in, I3, I'm sorry, that's I5 coming in, I6 is leaving, and I4 coming in. So KCL, what do we have? We have I2 coming in, plus I4 coming in, plus I5 coming in, minus I6 going out is equal to 0. All right, I2 from the top. Do we know it? No. So what did we do? We went from A, so it's VA, got to B, minus VB, divided by the resistor it hit was the 2 ohm resistor. All right, I4. We know I4. That's good. I4 is the 6 amp source, so he's 6. I5. We know I5. That's the 3 amp source, so that's good. 3. I6, we don't know. He's leaving, so he's minus. We start at B, and we go to the ground divided by 4 is his resistor. So there's his equation. Again, two unknowns, A and B. So let me get this into standard form just as before. Multiply by 4, we'll get rid of all the denominators. So the first one has 2 left over, 2VA minus 2VB. 6 times 4 is 24. 3 times 4 is 12. 4 divided by 4 is 1, so I'm just left with minus VB here. Is equal to 0. All right, standard form. We have 2VA minus 2VB minus VB is minus 3VB is equal to negative 36. And so there's his equation. So, last step, calculate A and B. How do I do it? This time I'll use Cramer's rule. Last time I did substitution, this time I'll do Cramer's rule. You can use substitution here if you want, that's fine. So Cramer's rule, let me just block things off so we can see it clearly. First thing I want to do is I'm going to rewrite the equations on top of each other so I can see them clearly. We have minus 8VA plus 5VB is equal to 60, and 2VA minus 3VB equals minus 36. So I want to make my three matrices. The W is just the coefficients, so minus 8, 2, 5, negative 3. Then we have the VA, which will be 60, negative 36, 5, negative 3. And we have the VB, negative 8, 2, 60, negative 36. All right, so those are my three matrices. Now, to solve for VA, I do the determinant of VA over the determinant of W. All right, so determinant of VA, I do the cross multiply and subtract. So 60 times negative 3 is negative 180, minus 36 times 5 is 150 plus 30 is negative 180, divided by W. Negative 8 times negative 3 is 24, minus 2 times 5 is 10. All right, so negative 180 plus 180, well, this is just 0, so VA is 0. All right, what else? VB. It's the determinant of VB matrix over the determinant of the W matrix. What is VB? So negative 8 times negative 36, we get 288. Minus 2 times 60 is 120. Over the W, well, the W is 24 minus 10 is 14. So 288 minus 120 gives me 168 over 14, which is 12. And there we go. VA is 0, and VB is 12. So, interesting, one of the voltages happens to be 0, but that's just the way the circuit was drawn, the numbers chosen, things like this. The voltage at A is 0, the voltage at B is 12. Now remember, as is true for all of these aren't the actual voltages at A and B. Those are the voltages relative to the ground being set to 0. So again, if this is part of some bigger circuit, and so this is connected to some other piece, if it's connected where the ground is, then maybe the ground isn't really at 0, maybe it's actually at 10 volts. So if that's actually at 10 volts, then VA is 0 plus 10, which is at 10 volts, and VB is 12 plus 10, which is 22 volts. So always keep that in mind, especially if this is, something you're going to be doing experimentally or in a lab or something. These theoretical calculations you're getting are relative to the ground. All right, so I want to do one more example. Example 3. Say this is our circuit. All right, so we have, let's say, 10, 5, 2, 4, 6, and 8. So here's our circuit. What's the first step? Choose a ground. So as usual, here's our ground. So all this bottom stuff down here is the ground. Next, label the nodes. Let's see, what can possibly be the nodes here? We've got, here, that's a node. We'll call that A. This is a node. We'll call this B. And notice we have a third node this time, C. So in this problem, we actually have 3 nodes to worry about. Well, that's fine. You could have any number of nodes. You could have 1, you could have 7. It just depends on the circuit. Here we have 3. Fine. Next, currents. So as usual, we've got I1, I2, I3 for A. For B, I2 is still coming in, so I2 is still there. Let's say I4 is leaving B to the right. I5 is leaving B down. And then for C, I3, which went up from A, hit the 8, and now comes down into C, so I3 is still there. I4 left B, moving to the right towards C, so I4 is still there. And of course, I6 leaves C downwards towards the ground. All right, so again, for every node, all the wires coming out of the node are going to have a current. Some are coming in, some are coming out. You choose the direction. Of course, if the current source is on that branch, then you know the direction. But if you don't, you just choose one. So that's done. Now, last step, write down my Kcl equations for each node. All right, so let's do it. Let's take node A first. Node A. So what's going on at A? Well, I1's coming in. I2 is leaving to the right. And I3 is leaving up. Equal to 0. There's Kcl for node A. Now I want to rewrite the i's as v's over r. So I1, do I know the value? Yeah, I1 is a current source of 10, so that's easy. What about I2? Note, so I got to do V over R for him. I2 went from A to B, so VA minus VB, divided by the resistor, which is 2. I3 leaving A, no, he's not a source, so I got to do from A, he went to C, and he traveled through the 8 ohm resistor. And there we go. Now, because this is a 3-node system, the algebra at the end is going to be long and tedious. So just like what happened with loop analysis, in this case, instead of going through the calculation, I'm just going to want you to write down the equations. So, and when I mean write down the equation, I mean write them down, simplify them as much as possible, and put them in standard form. You know, all the unknowns on one side, all the numbers on the other. So, let's take this. I want to get rid of these denominators. I have to multiply by something that cancels out all the denominators, so it has to be common. In this case, 2 and 8. 8 is common, so I'll multiply everything by 8. So 10 times 8 is 80. 8 divided by 2 is 4, so 4VA plus 4VB. 8 divided by 8 is 1, so I have VA plus VC is equal to 0. Standard form, we have minus 4VA plus, minus 4VA minus VA is minus 5VA plus 4VB plus VC is equal to negative 80. So there's node A's equation, standard form simplified. All right, now we'll look at node B. Same thing. We have I2 coming in, minus I4 leaving, minus I5 leaving, equal to 0. I2 is not a source, so what did he do? He went from A, got to B. So VA minus VB over his resistor of 2. I4, he's not a source, so he went from B to C. So VB minus VC over 6. And 5, not a source, so he went from B to the ground over his resistor. All right, again, simplify this. I'm going to multiply by something common to 2, 4, and 6. And so what's common would be 12. So I'm going to multiply everything by 12. 12 divided by 2 gives me 6 left over, so 6VA minus 6VB. All right, 12 divided by 6 is 2 left over, so 2VB plus 2VC. 12 divided by 4 is 3 left over, so 3VB is equal to 0. All right, as before, standard form. So I have 6VA minus 6VB minus 2VB minus 3VB is minus 11VB. And plus 2VC is equal to 0. So there is the equation for node B. Last node, node C. What does he have? I3 coming in, plus I4 coming in, minus I6 leaving. It's equal to 0. All right, what was I3? I3 came from A and went to C. So VA minus VC over 8. What was I4? I4 came from B to C, so VB minus VC over his resistor is 6. And what was I6? I6 is a current source of 5, so 5 equals 0. All right, so how do we get rid of these denominators? What's common with 6 and 8? 24 is common. So I'll multiply everything by 24. All right, 24 divided by 8 gives me 3 left over, so 3VA minus 3VC. 24 divided by 6 is 4 left over, so 4 VB minus 4 VC. And then 24 times 5 is 120 is equal to 0. Standard form, 3VA plus 4VB minus 3VC minus 4VC is minus 7VC is equal to 120. And here's my three equations. Now I'll just rewrite them down here, just so they're all in line. I had minus 5VA plus 4VB plus VC equals negative 80. Then I had 6VA minus 11VB plus 2VC equals 0. And 3VA plus 4VB minus 7VC is equal to 120. Now, of course, if I wanted to, I can now take these three equations, use Cramer's rules to calculate VA, VB, and VC, and I'd have the actual answers. But just to skip the tedium of the algebra part of this, this is what's important. Can you take a circuit and analyze the circuit using this technique to set up your equations to be able to calculate these unknown voltages? So this is nodal analysis. Now, there's one extra complication that I haven't shown yet, which the next video I will show. And that complication involves what happens if you have a voltage source inside of the circuit as well. As you can see, none of the examples I've worked on had voltage sources at all. They all had current sources, but no voltage sources. But you can do nodal analysis when voltage sources are involved, and I'd like to show you how to do that. But that'll be another video. For now, these fundamental nodal analysis, these more basic nodal analysis type problems, you should now be able to do. You've seen examples where you have one node, two nodes, three nodes. You've seen how to label the nodes, you've seen how to label the currents, how to set up the equations, how to solve the equations. So now it's up to you to practice them. Can you sit down with a blank sheet of paper, given a circuit, and analyze it yourself without following along someone else doing it for you? That's the key. Once you can do that, then you know you're golden on the test. But until then, you need to practice to gain that experience to be able to be comfortable with this stuff. So I hope this has been helpful. If you have any questions, of course, email me, let me know. Until next time.